Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And this is part 6 of an 11-part little mini-series within that playlist. This little mini-series deals with hierarchical designs. And here we're going to look at a random effects model and the distributions associated with the sums of squares and the f-test. So as a reminder from parts 1 and 2, the model is y equals x star, beta star plus epsilon. So it is a linear model, but we partitioned it into the the grand mean, factor A, and factor B. And one big note that B is nested within A. And then all the parameters, epsilon, beta, and alpha, are normally distributed with mean 0 and then their own variance. All the alpha, beta, and epsilons are all independent. Now, if we were to take the mean of this model, the expected value of y, it goes into each term here, and this is constant. This is constant. This is a random variable, but it has a mean of 0, so that's 0. This is mean 0. That's mean 0. So the mean of our model is mu times a 1 vector. Now the variance of y is we take it into this is, since this is a constant, it goes away. And I actually have a video called Random Vectors and Matrices, where we look at the mean, the variance, and etc. covariances for random vectors and matrices, if this is a little bit unclear for you. But it goes into each term, and there's no covariance because they're independent. And you take the variance of this, and now the x comes out front and then it's transposed out back, and we take the variance of alpha, which is sigma alpha squared times I, and we get this. Same way for the beta term, and the epsilon term is just sigma squared I. Now this kind of looks like the perpendicular projection matrix onto that comp space if we divide it by Bn. But if we do that, then we have to multiply it by Bn. And so that brings it to this. And I do this because when we end up multiplying things together, it's easier for me to see the results when we're dealing with these perpendicular projection matrices. And now the same way for this second term. The x comes out front, it's transposed out back, the variance of beta, we get this. And then it's very close to the perpendicular projection matrix onto that column space if we divide by n. So then we have to multiply by n, then we get the perpendicular projection matrix. Variance of epsilon is just sigma squared I. So this is the variance associated with the model. Now the expected values of the sum of squares for alpha, which in matrix form, and we derived this in the last video, or maybe either part 4 or part 5. And so the expected value of this quadratic form here, and I have a playlist called Quadratic Forms where we derive the mean, the variance, and the covariance of quadratic forms. And there's a formula in there that it says this expected value is the trace of this matrix times the variance of y plus the mean of y times that matrix times the mean of y, and that transposed. Well, the mean of y is mu times that 1 vector, but this projects orthogonally onto that 1 vector, so this is 0, and we're left with this. So now we have the trace comes down, the matrix, and then this variance right here goes in here. Now this matrix times this, since this lives in the column space of x and this projects on the column space of x, we get it back. So this is multiplied by to here, and m is since x alpha is a subset of m beta, this projects back on, this will be projected back onto itself. And so this matrix times this is just m alpha minus j. And then I, we just get this matrix back. And then you factor out this m alpha minus j, and we're left with this. So this constant times this matrix. So So the constant could come out front, and the trace of m alpha minus j is a minus 1, a minus 1. Now, in one thing to remember is that this step right here is that matrix in the middle. This is the variance of y, and it reduces to a constant times that matrix. And I'm being a little overkill with that step, but it's going to help us when we get to the distribution of the sums of squares here. Now, the sums of squares associated with beta, or factor b, and which is nested within factor a. Here's the quadratic form. So it's going to be the trace of this matrix times the variance, which is this. And then it ends up being this matrix times the mean. You know, something very similar to this. But the mean of y is 1, and this projects orthogonally onto that. So it's 0. So I left it out, mainly just to save space. So then this matrix projects onto column space of x beta, but orthogonally to x alpha. So this right here and this goes to 0, and then this times m beta, you get m beta minus alpha back, and then that times I, you get it. So then you factor it out, and we're at this step. This is constant, so it can come out front, and then the trace of this is going to be ab minus a, which is what we get here. And then now the expected value of the sum of squares there. Now remember, the sum of squares there, and I didn't write the quadratic form here. It's y transpose I minus m y. So then it becomes the trace of that matrix in the middle times the variance of y. And then this other part here, which I also left out, goes to 0 because this projects orthogonally onto that one vector. So it's 0. Now, I minus m. So m projects onto the column space of x star. I minus m projects orthogonally onto that. And so since each of these live in that column space, this is 0, that times m beta is 0, and we're left with just this. Now sigma squared comes out front. The trace of I is going to be a times b times n, and then minus a times b, which is what we get here. Now, when we look at the distributional properties of these three, and we're going to need to do that so we can conduct f-tests. And I have a playlist called, quadratic forms, and in there we talk about the distribution of quadratic forms. And y is multivariate normal with this mean and this variance. And in that setting, we have to make certain that certain things are met, or some of the requirements or assumptions are met. And so one of the assumptions, now we're going to look at, it deals with this one. I do it kind of oddly in this video, and I wish I could take it back, but I didn't, and it'll all make sense in a second. So we need to make sure that this divided by a constant times the variance of y, so just call this a, and then this, of course, is the variance, is idempotent. But remember, this m alpha minus j times the variance ended up being this constant times that matrix. So that constant cancels with this, and we're left with just m alpha minus j, which is idempotent. So then the rank of a times the variance of y is just a minus 1. A minus 1. Now, the variance, looking at this, so this m beta minus alpha divided by this constant times the variance of y, just call it b times the variance of y, ends up just being this, right? Because this matrix multiplying the variance ends up being a constant, which is this constant. It cancels, and then we're just left with m beta minus m alpha. This ends up, the rank of that is a times b minus 1. This here, so I minus m times the variance of y divided by sigma squared. This piece right here ended up being sigma squared times I, or this ended up being sigma squared times I minus m. The sigma squares cancel, and we're left with I minus m, which is idempotent. And the rank of this is the rank of this, which is ABN minus AB, which is this. Now, in our F test, we have to show that the numerator and denominator are independent. And so to do that, these three multiplications we need. And so this projects orthogonally onto the 1, so that's 0. This is 0. And this is 0, because they all project orthogonally to 1. So now, if we look at this sum of the squares right here, and based upon the fact that if this is thought of as y, then what we just went through, it's easy to show that it's a central chi-squared with a minus 1 degrees of freedom, right? And then this, and you have to go to the theorems in the quadratic distribution of quadratic forms. Then it's easy to show that this sums of squares is y transpose by, which is a central chi-squared with a times b minus 1 degrees of freedom. The sum of squares error divided by sigma squared can be shown to be a central chi-squared with ab times n minus 1. Now the F test is that there's no factor A effect, means that variance is 0, versus there is an effect, which means it's positive. And the test statistic is the mean squared for alpha divided by the mean squared error for beta. Now, one thing and under the null hypothesis, this is a central F distribution with a minus 1 degrees of freedom and ab minus a degrees, denominator degrees of freedom. And this is under the null hypothesis. And so why is that? Well, this piece here is not a chi-squared unless you divide it by this, right? Then that becomes a chi-squared. And the sums of squares for beta nested within alpha is not a chi-squared unless you divide by this piece. So, but under the null hypothesis, sigma alpha squared is 0. So this drops out. And then we're dividing by the same thing, and that's 1. So it cancels in the formula under the null hypothesis. And so to test the factor B effect is sigma beta squared is 0 or it's greater than 0. And we use the sums of squares for beta nested within alpha divided by its degrees of freedom, which is the mean square for beta. And this is the mean squared error. And under the null hypothesis, it is a central F distribution. All right, well, that's all I have for this. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.